Welcome to the shop. I'm continuing to make parts for NQALHA Production Run 4. There's 750 parts to make, so I better get busy. Today's part is going to be the most complex and challenging and difficult and just almost insane part in the entire project. It's going to be hogged out of 1-inch thick aluminum, leaving only a small shell remaining with some fairly complex inner structure. This will form the housing for the microprocessor-based custom circuit board that controls the unit. This design is mostly known and trusted. It's mostly the same design as used in previous versions, but I made one small improvement to try to improve the conduction of heat from the motor drivers into the case and heatsink. And no, the previous design didn't have an overheating problem. I never got one back. I never received a report of overheating leading to failure, but you know, I always like to just improve whenever I can, and I had an idea for, hey, if I put this extra little bit of aluminum in, then I might get a tiny bit better heat performance. And I tested this on my prototype on my personal NQALHA and verified with the thermal imaging camera that yes, in fact, it does improve things a bit. So I'm going to be running the next 10 parts using the now tested slight improvement over the previous design. So I've already set up the machine. I've got the corners indicated with the Heimer indicator, the zero set using the Tormach electronic tool setter. If anybody is interested in seeing details of how this is done, the first two videos in the series show it in detail, but for now it's just repetitive, and I'm going to try to eliminate some of the repetitive stuff from these videos. Also, this is a part that requires all 10 tools to be installed in the tool changer. And I just got the screws in yesterday to replace the broken screws when the last time the tool changer misbehaved. So now tool changer is back in action. Things should be working really well. Tool path should be known and trusted, but as always, I'm going to be very, very careful with this one. Now, in most of my parts, I try to do the tapping operation last because that way I can blow off the chips, blow off the coolant, open the door, and be able to apply the Tap Magic cutting fluid. In this case, because the part has such a long machine cycle, I don't want to get all the way to the end and then break a tap and waste all that time. So I'm tapping early because this part actually has 632 and 440 taps, which mostly behave well, but I'm always a tiny bit concerned about machine tapping and breaking taps, even though I've run many, many of these parts without breaking a tap. It's just, I modify the sequence. There's really almost no downside to modifying the sequence. And if something goes wrong, well, I don't have to waste a whole lot of time and wear on the machine and the cutter milling a part that's just going to go in the trash. So here we go. Now, one more comment. Since the part involves hogging out a large pocket out of thick material, you're not going to really see very much in the video other than a puddle of liquid and a head moving around. So I'm going to periodically pause the tool path and do a kind of a close-up of the stages to get an idea of what happens at each level. This part, the toolpath was constructed in multiple levels. Even though it is a three-dimensional part, the toolpath was calculated as a sequence of two-dimensional toolpaths, each one at a particular level. And in between levels, I'll blow off the coolant and get a close-up view so you can see what, okay, well, that's what that level looked like. But first, let's drill some holes. .632, using a stubby drill, a screw machine drill, so that I get an accurate placement. Okay, let's get the squirters in place. Pre-feed looks correct. Feed looks correct. Fast peck cycle, 5,140 RPM, 10 inches per minute, 50 thousandths per peck. Precisely aligning these lock lines is somewhat challenging. They tend to spring back a lot. Okay, here comes 632 Taparoo. Let's get tappy. Since these are blind holes, I'm going to go ahead and waste a little bit of tap magic by filling the hole completely. This provides a little bit of hydraulic pressure to further force the chips out of the blind hole. I'm using a spiral fluted tap, and the spiral fluted tap ejects chips up out of the hole. I'm also drilling the hole substantially deeper than the tap. I'm doing all this stuff to avoid tap breakage because, as anyone who's ever used a 632 tap knows, they can be a troublesome little tool. Actually, in some ways, because of just the geometry of the tool, a 440 is actually easier to tap than a 632. 632 is a troublesome little tap. Okay, so now we're going to switch to the aluminum shredder. This is a 3-flute solid carbide roughing end mill that produces extremely fine chips. And when doing a deep pocket like this, it's really important to get good chip evacuation. And so the combination of flood coolant and the hydrodynamic forces generated by the cutter as it rotates in the pool of liquid, combined with the very fine chips, result in excellent chip evacuation with inferior coolant, like, whatever. I'm not even going to name what would be inferior, but if you have insufficient chip clearance on a standard end mill that's producing large, gnarly chips, you can end up recutting the same chip multiple times, building up, welding the chips to the end of the cutter. Cutter stops cutting, break the cutter, ruin the part. So the aluminum shredder works exceptionally well for this kind of work. Everything's looking good. I'm ramping in to try to somewhat avoid buildup on the end of the cutter, the rat nest on the end of the cutter. I'm using what the Bobcat calls the adaptive advanced roughing cycle, and this is similar to the type of tool path used in high-speed machining. I'm also observing the spindle load on the spindle meter, which you can't see in the video, and observing that the spindle load is low, so I might be able to increase the overlap in the cut, which I've done on previous parts, to try to get a little bit improvement in cycle time. So let's see if now. Not the right time. I've never done this before, trying to do a feed hold in the middle of the cycle. Okay, coolant off. Get the old handheld camera here, and that is what the first level pocket looks like. So I'm going to put the camera back on the shelf. Coolant back on. Second level. I haven't yet tried. I do have the part modeled in SolidWorks. I do have a solid model of the part, and Bobcat will generate a tool path based on a solid model. I haven't experimented with doing a 3D, full 3D tool path on this part. I don't know, might work better, might be faster, but at the moment this is a sequence of 2D tool paths, and as it gets deeper, they get more complex, because there's more internal structure that needs to be cleared. So we're starting to create some internal structure. I've got a little bit of a boss beginning to form, a little raised area. These will end up being the mounting points where the circuit board is attached. They're also the points where the 440 screws are going to be drilled and tapped. Okay, so now my memory is getting a little faulty. I remembered that at this point I was going to do the 440 tap, but sometimes Bobcat, either I misremembered or Bobcat just sometimes changes machining order for reasons only it understands, following along with my philosophy of tapping early in case the tap breaks. I probably should have tapped at that point, but of course that introduces a tool change, and I don't know. Hard to remember back to when I designed this tool path. Spindle power meter is showing almost no spindle power, definitely nowhere close to exceeding the ability of the spindle. So, coolant off, getting a little bit of buildup, a little bit of rat nest. So, now we're starting to see the new feature. This little rectangle is the newly added feature. The little rectangle will be actually in contact with the surface of the motor driver ICs with a little bit of thermal paste to be able to more efficiently transmit heat from the case of the motor driver into the aluminum body, and then the aluminum body, of course, is the heat sink itself, but its new cover now has heat sink fins milled into it, resulting in overall better thermal performance. This part requires 5 operations: the pocketing with internal detail, the outside perimeter, and then milling and drilling on various different edges from various different angles, all requiring special setups, special fixtures, and as it gets toward the last operation, it starts getting really nervous, because if something goes wrong and the last operation is boogered up, well, then I've just wasted a tremendous lot of time. As the internal features start getting developed, the tool has to do a lot more rapid motion to get up and over and around the various different internal features. The finish pass will be done with a 1/4-inch end mill, because some of the internal radii need to be reasonably tight. Getting this whole thing to fit has proven to be a real challenge. So, get the camera here and show I'm starting to develop that little square guy that you can see kind of hanging off at an angle. That is the mounting surface for the lever. And the lever on the handle is the part that releases the magnet when you want to move the head around. There's a hole drilled perpendicular into that angled face and tapped with a 1024 tap, and that hole is one of the most critical dimensions in the entire unit, and it's very difficult to get right. I find that I often need to take a few thousandths off the tip of the lever to kind of hand fit, because the lever needs to be within a few thousandths to get the correct feel. And I'll be discussing that later when the lever is machined and when I get around to assembly. And yes, I am going to video the assembly as well. So that completes the roughing operation. See, there's a little boss over on that side. The heat transfer rectangle, the boss for the mounting surface for the 440 screw, and then, come on, focus, and then the block that will get the tapped hole to put in the shoulder screw for the lever. So let's see what happens next. See how good my memory is. I think it might be the drill operation. Nope. Gonna be the finish pass. Pre-feed looks correct. Feed looks correct. I'm doing the finish pass, even though the finish pass is only taking 15 thousandths. With that long end mill, I've actually broken an end mill, even with the flood coolant and a 15 thousandths pass, if I try doing it all in one full depth, because the pocket is 0.9 deep, almost all the way through the 1-inch piece. And that quarter-inch, this is a quarter-inch long flute, 3-flute, solid carbide, Lakeshore carbide end mill, and it can't quite make it in a full 0.9 depth pass, taking off 15 thousandths along the entire depth of the cutter. The finish operation is being done in a specific order because some of in particular, that little round boss where the circuit board mounts, any burr around the edge needs to be removed, and it's a rather difficult burr to remove by hand. So I use the finishing cutter to just barely kiss the edge to try to get a little bit better machine deburring so that there's less to do by hand. This results in a fairly slow finishing cycle, but it produces a good part. Did I mention this is the most complex part in the entire process with the slowest cycle, and probably not the most number of secondary operations, but certainly the most complex third, fourth, and fifth operations. So finishing continues. Many levels, very conservative, 5,140 RPM, 20 inches per minute, because even if I don't break the cutter, if it starts chattering, I end up with a very poor internal surface finish. So I'm taking it easy, taking it conservative. I may go in the CAD room after this and bump up a little bit, like 1 notch, bump up the roughing aggressiveness a tiny bit. So now I'm cutting a slot in the bottom. This is the slot that the lever will protrude into. So now all of the liquid drains out, and when I look, I see no chips. As the coolant drains out, I see no chips remaining in the part, and that shows me that the chip evacuation is actually working correctly. So now I'm going to drill 1/4 inch hole. Should be a fast pick, I'll optimize that. The 1/4 inch hole is where the wires come. The wires go through the center of the handle over to the control portion. This is where the circuit board is. The other side is where the buttons and speed control are, so they got to get wires going to them. Now we're drilling the 2 mounting holes. And yeah, I probably did, either I did or Bobcat did, leave the 440 for last. So, always an interesting debate. Actually, this is not the 440. This is the 1032 tap drill for the mounting hole that mounts the controller housing to the side plates. So now we get Mr. 440 drill. Doing a full peck cycle here, which is probably a good idea given that the drill bit is so tiny. Just checking to make sure that I have sufficient clearance with the old eyeball. And we do. Just barely. I'm using a stubby drill bit, a screw machine length drill bit, because it tends to align itself better without walking around on the part. A long drill bit without a pilot hole will tend to walk around a little bit. So now .440 tapped hole. Fill that hole with tap magic and hope for the best. Actually, I only broke a tap once in the 440 operation, and that was my mistake. Okay, first operation is successful. And let me show the part here a little bit. Quite a complex little part. So, for the second operation, and I might as well just go ahead and show it right now. When I combine them into a combo toolpath, I'll have like one part waiting on the prep table, already been deburred and cleaned and ready to go, and while a first operation and a second operation are in progress. But just to show you right now how the second operation is done, I've got a tooling plate with two precisely made steel pins that fit the holes in the bottom. I'll go ahead and deburr this. Normally I'd be deburring while another first operation is in progress, but just to be able to continue with the video right now. So, fits nice and snug using a little aluminum washer on the hold down screw. And that's interesting. I may have to, yep. I'm going to go ahead and use just a regular screw without the little washer to get this demo done. And, you know, it's not a cosmetic surface. I really don't care that much that I booger it, but the pins are closer together on this part, and I really don't have room for the aluminum washer. Go over here and load up the tool path, and like always, this is a known trusted tool path, but I'm going to check it anyway. Looks like it's moving to the correct work offset. Looks like it's moving to the correct pre-feed height. I'm going to turn off the coolant. Check it with the old eyeball. Things are looking good. Using a 1/2-inch end mill, 3-flute, solid carbide, zirconium nitride coated. And the reason that I'm using a 1/2-inch end mill is actually two reasons. That I want the stiffness of the end mill because I'm going to be milling a 1-inch face on the finished cut, and the finished cut is very definitely cosmetic. It's one of the most important cosmetic features on the unit, and so I want it to come out really nice without chatter. And when I'm cutting a 15 thousandths pass on a 1-inch surface all in one pass, with full contact of the entire flute length, I want the cutter to be really solid and not have cutter deflection or chatter, so that's why I'm using the 1/2-inch. So here comes the finished pass, 1/2-inch. Oh, I am getting a bit of chatter, which is very surprising because last time I ran it I didn't. Chatter on the Tormach is mysterious. Sometimes it's there, sometimes it isn't. Sometimes it goes away like magic. I bet next time I run the part, I don't get chatter. And even with yeah, I don't know. I was gonna say, even with the chatter, the surface finish is excellent, but not really. Surface finish is a little less than I'd like it to be. I'm gonna check a bunch of stuff and just make sure everything is working correctly, but I haven't gotten chatter before using the exact same toolpath parameters. Here's the finished second operation part with nice rounded corners, mostly beautiful surface finish, a little bit of a chatter problem. So I'm gonna go back in the CAD room. I don't think it's necessary to show the combo operation again because I pretty much have showed everything that there is interesting to see in the first two operations. So I'll be back for the third, fourth, and fifth operation. So see you later. First and second operations have been complete, and I changed out the vice jaws. So now I have the tall jaws, work offset 2, Z0 on the vice surface. And now it's time to cut a slot in the bottom of the part. And I need to be really careful here to make sure that I put the part in the vise correctly. It'd be really unfortunate to make a stupid mistake at this point. This slot will provide access for the wires and the connectors that are on the circuit board, as well as providing access for the drill that needs to drill at an angle through the clearance hole and drill the hole for the shoulder screw that acts as an axle for the lever. This is one of the trickier parts of the operation, as you'll see as the video proceeds. But right now, I'm going to cut a slot. And this should go really fast. And hopefully correct, because this is a known trusted toolpath. Verifying that it looks like work offset is correct. It looks like the position is correct as far as I can see with the old eyeball. Pre-feed height is correct. Everything is looking good. 1/4-inch end mill. Cutting fairly slow and conservative. Probably could go faster, but at this point in the operation, having spent so much time on the first operation, hogging out the cavity, I tend to go really careful on the remaining operations. Just, it's a short operation, even at a slow speed, and, you know, it doesn't hurt. So, looks completely correct. Now this, get the part in the camera view. There's a good view. So that's what it looks like. And I'm going to turn the camera off, run the entire set of 10, and then come back for the fourth and fifth operations. Third operation is now complete, and everything worked well, and the parts all look really nice. I do have a couple of comments on the part of the work that I did off camera, completing the run of first and second operation. First off, Bobcam can make you crazy. The toolpath that I constructed for the for the pocket and the internal complex detail, that toolpath was a fairly complex toolpath that the order of operations was really important. If you're doing one layer, then the next layer, then the next layer, then the next layer, you got to make sure you don't try to do the last layer first. And as I was attempting to make minor changes to improve efficiency, BobCAD kept changing the layer order, and it even just completely eliminated a couple of my tool paths, forcing me, fortunately I didn't ruin any parts, but I did notice that, oh, that little operation on that part was missing, so then I had to make a custom toolpath that contained only the missing operation, and it made the whole thing take a whole lot longer. So software can make you crazy. Second thing is, the chatter was completely controlled. The first part that had chatter, I was able to remove it all on the Scotch-Brite wheel, and then the chatter on the Tormach is mysterious. Sometimes it happens, sometimes it doesn't. Same material, well, not at this exact same material, but aluminum 6061 from a different batch. Sometimes it chatters, sometimes it doesn't. Same feed, same speed, same cutter. Who knows, the cutter may have gotten older, whatever. So what I did here was I reduced, and sometimes chatter is a resonance that occurs at a particular combination of feed and speed and cutting depth and a bunch of other things that I don't even remember what they might be. So I tried reducing the spindle speed a tiny bit from 5140 down to 4500. Chatter went away, surface finish is beautiful, just astoundingly beautiful. So I'm moving on now to the fourth operation, which is also a very simple and quick operation, but at this point in the process, if something failed and I had to scrap a part, it'd be a pretty annoying thing. So I'm going to be drilling a round hole and cutting a small slot with an 1/8 inch end mill. And you know, things go well. I haven't had a problem yet, but still gonna be real careful about this just to make absolutely sure. Finger on the stop button. Single block mode. Loading up the tool. Looks like it stopped at the pre-feed height. Feed height. Drill that hole. Boy, what an exciting hole that was. And then 1/8 inch, 2-flute, end mill. Wish I had a faster spindle, because the 1/8 inch guy really wants to run a lot faster. But I just use a insanely slow feed and hope for the best. 5 inches per minute, 5,140 RPM. Gotta treat that little guy carefully. So there is, let me get this in the camera view, very successful fourth operation, no problem at all. The little slot is for the USB micro connector on the edge of the controller board. Now, you might ask, why does the NQALHA have a USB connection? Well, it's a long story, and I'm not going to tell the whole story here on the video, but I put the USB port on partly because I got it almost for free. The controller has built-in USB, and it only cost me a connector and a couple of capacitors. When I started the project, I anticipated that there would be a need for a user interface. Back when, in the early versions of the software, it had functions that needed configuration that a user interface might be useful for. As the project proceeded, those functions kind of went away, and the entire reasoning behind them kind of went away. I still use the USB port for troubleshooting, for debugging, for development, and there's a possibility that it's someday in the future the USB port may be usable for something. I don't know what yet, but it's in there. It doesn't cost anything. It doesn't cause any problems. So that's why the NQALHA has a USB port and why I cut that little slot with the 1/8" end mill. So turning the camera off again, gonna run the batch, and then the final operation will be a kind of a tricky one. It's drilling a tap hole for a 1024 tap through a clearance hole into the inside of the part using a special fixture and trying to get the hole as accurately as possible. Another couple of comments. I've been trying to improve my production accuracy on these parts, and accuracy is limited. The Tormach is not a super highly accurate machine, and there's probably, I don't know, maybe some slight errors or imperfections in my approach to machining, and who knows, maybe it's possible to get more accuracy out of the machine. I haven't figured it out yet. And as a result of all of that, I ended up having to hand fit the levers to get them to feel right. And of course they all do. I'd like to either eliminate or minimize the amount of hand fitting that I do, because hand fitting takes a long time. So I'm attempting to use my measurement instruments and try to keep this process a little bit more under control and see if I can hold a little bit tighter tolerances to either avoid or minimize the hand fitting. So, see you later. The fourth operation was completed successfully, and now I need to do the fifth operation, which is somewhat tricky. So here's what's going on. Let me get this in the camera here. I need to drill a hole through this clearance slot into the face of this guy and make sure that I have sufficient stick out that I don't run the collet holder into my nice finished part. This is a tricky one. I really don't like, I wish I could figure out a way to do this better. I really, really don't like long drills, long, thin drills without a center hole, but I can't imagine a way to get through that clearance with a spotting drill unless I made the clearance really gigantic, and I'm not sure I want to do that. So I'm using a special fixture that aligns the part in place. So there's what the fixture looks like. And let me store that tool. Normally, when I do my 1024 tap holes, I use a stubby drill, a screw machine length drill. So I've switched to a jobber length drill, and I have to reset the tool length. So let me go over here to the tool offset, 45, and using the Tormach electronic tool setter, I'm going to reset the tip of that tool. I have used a special drill cycle that I believe is going to help a little bit. So I rapid to get the tool tip in roughly in position, feed slowly to get it so it's kissing the top of the material, then feed very slowly at a ½ inch per minute to just make the tiniest little dimple to kind of hopefully give me a center punch mark before starting the normal peck cycle. And this hole getting this hole accurate is the key step in eliminating or reducing the amount of hand fitting I need to do on the lever. I'm not super optimistic that this run is going to be any better than the previous runs. I've had to hand fit every run that's ever been done, and I anticipate that I'll have to hand fit this one. But every time I do a run, I try to get it just a little bit closer and try to be maybe a little bit more clever, come up with a little bit better idea. And, you know, who knows, maybe I could machine a little drill bushing thing that I could like insert inside the body that would guide the drill a little bit better, but oh well. This is what I have today, and I'm just going to go with it. So this is always a slightly scary tool path to run. I'm going to that does not look right at all. Come on. What's going on? Memory is so faulty. And I actually had it written correctly on my setup sheet. I didn't read the damn setup sheet. That's why I double check, triple check, check the check, and check again. Y0 is not the way it was for the previous two parts, which is the vice jaw surface. It's the fixture surface. So double check, triple check, check again, check the check. And even then, sometimes things go wrong. So in goes the Heimer. using the Tormach jog shuttle controller to very slowly move the axes. The jog shuttle controller kind of works. I really don't like it. To me, it's a bit of a borderline design. I find it not very intuitive to use, and I discovered too late, not even expecting it, the jog shuttle controller has a button that chooses the step size when you're stepping with the step wheel, and the step size can vary all the way from 1/10 of a thousandth all the way up to 100 thousandths. And I guess inadvertently something happened when I was cleaning off the tabletop with the compressed air or reaching for the keyboard. The step button inadvertently got pressed, resulting in the step being set way too high. So when I went to adjust the Heimer using the step wheel, thinking that I was moving in tenths, I was actually moving in tenths of a thousandth. I was actually moving in tenths of an inch, and pingo goes the tip of the Heimer. I hate when that happens. Fortunately, the German engineers at Heimer were anticipating problems like this, and the indicator tip has a sacrificial section of plastic so it doesn't destroy the entire indicator. So here we go again. We're going to try one more time, and let's see if we can get this pig to oink. Single block mode. Move to what I hope is a Mobetta position. I stopped the operation because it's gonna rapid down through the clearance hole and approach the drill face, and I wanted to kind of stop it once it's gotten into XY position and then manually jog the Z down. I don't know if you can see that on video, but it barely clears. And of course, since that clearance slot, since it's at an angle, was designed to be just barely big enough for the drill to get through. So, okay, wish me luck. Gonna try it for real. Okay, it cleared. It did not have a collision. I'm gonna set this part up on the surface plate with an indicator and if you can see in there, I'm gonna set this part up on a surface plate with a gauge pin and a precision indicator and see how accurately I actually drilled. And hopefully they're getting a little better. But that does it for today's video. And thank you for watching. It's been fun.